Welcome, everyone, to the next installment of the SMART series, Gaining Mastery of MIS Inguinal Hernia Repair. Today, we're going to be delving into part 2 of a 4-part series. Today's topic is mesh essentials. We have a featured speaker today. I think you'll be very excited to hear. Jonathan Thomas is the principal R&D engineer at Medtronic, and he'll walk us through everything from the molecular basis of polymers to textile and structural design to the host response. So Jonathan, take it away.
Thank you, Dr. Laurier. As Dr. Laurier said, my name is Jonathan Thomas, but I go by the initials. My nickname is JT. I've worked at Medtronic Research and Development for the last 13 years, and I'm located in North Haven, Connecticut. For those of you who are not as familiar with the Northeast US, that is right between, pretty much halfway between New York and Boston. At Medtronic, I've worked on sutures, hernia meshes, and instruments for mesh fixation. My field of training and background and graduate research was in material science and engineering. When we talk about mesh properties, we like to connect outcomes to attributes. It all comes down to the interplay between the mesh and the host tissue. Specifically, there's a desire for rapid and complete integration of the mesh without excessive fibrosis. We do this by maximizing porosity and using biocompatible materials. The resulting repair needs to be comfortable, durable, and stable, and this comes from the mechanical properties of the composite repair. By composite repair, I mean this is a combination of the textile and the healing tissue. The biomechanical characteristics of the mesh are important. The last item that's listed there, visceral protection. This won't be discussed tonight, specifically because we're focusing on inguinal hernia repairs, but just to briefly talk about this, we believe that intra-abdominal meshes should be dual-sided, and we design them with dual components on either side to protect or to separate the textile from the viscera. As we look to a mesh, there are a number of design variables that we can adjust to achieve different properties. From these mesh properties, these parameters can be used for optimization for a specific application. Porosity can be driven by knitting pattern, mesh density or weight, as it's described often, multi-filament versus monofilament. Surface properties could be from the absorbable film, a coating, or the base polymer which the textile is made. The textile structure could be made 2-dimensional or 3-dimensional in thickness, and it could also be made with grips. And finally, the mechanical properties are driven by the polymer, the yarn that is chosen, and the knitting pattern. So this slide here is a simplified view. We want to get to the base understanding of how polymers are made. The example that we're using here is polyester. And when I say polyester, or the abbreviation of PET, this is defining it as polyethylene terephthalate. It's the most common polyester, and it's often just described to as PET. What happens with this is we start out with atoms, and that we can create chemical linkages between these atoms. They exist in nature. From this, functional units or chemical functions can be created between organic compounds. R would just be 2 different organic moieties. Right here is an actual ester linkage. We can take this and create what is essentially a monomer or a single repeat unit of an actual chemical structure. This right here is the terephthalate, the polyethylene terephthalate. Now, if we look at this, the polymer is made from taking multiple units of these MER units and polymerizing them. This is something we do in North Haven, Connecticut. We take an actual MER units and we process them to make them a full polymer. And by polymer, These are number repeating units, so that N at the bottom there in the polymer can be hundreds, thousands, even 10,000 units long. So the important question to ask is why different polymers are used for implants and specifically for hernia repair. Different companies leverage these polymers as differentiators through innovation, the different properties that they elicit when you put them in the body, and also some of them are patent protected. All polymers have advantages and different disadvantages. The properties stem from the carbon chains and the repeat units of these carbon chains. What happens is these repeat units can impart different stability and rigidity, strength and flexibility, durability, which is the ability for these polymers to last longer in the body versus others, and biocompatibility, and that drives how the cell material host reaction occurs. Specifically, if we're to look to these different polymers, there's 5 listed out on the right from their chemical structures. The top one you've seen before, that's the polyester, the polyethylene terephthalate. Right here is polypropylene. It's slightly different. It's just got one reactive or one side unit off of it, the CH3. Below is C2F4, and this is extended PTFE or polytetrafluoroethylene. This is the base material, and you classically know this as Gore-Tex or Gore material or Teflon. We look to the middle on the right. That is a chemical structure that you use during surgery often. This is a polymer of lactic acid or polylactide. This is used in a number of different hernia fixation products, as well as it's used in sutures extensively. And on the bottom right is another chemical structure. This is poly-4-hydroxybutyrate. Specifically, these ones on the right here and the one on the top are polyesters. They all belong to the polyester family, but they have different chemical structures. But on the bottom right is poly-4-hydroxybutyrate, as I said, but that's also classically known as Phasix and commercially as Phasix material. We want to talk about the polymers that are used by Medtronic. We have hernia meshes that are predominantly in the polyethylene terephthalate or PET range and the polypropylene range. We believe you can make a polymer out of both of these materials that is effective and safe and has good properties. Polyester brand or the polyester materials are used in the Priatex brand, Symbotex, and then also in laparoscopic ProGrip. In laparoscopic ProGrip, it serves as the base material as a monofilament textile. Polyester meshes were starting to be used back in the late 60s by Reeves and Stopa. If we look to polypropylene, this is the chemical structure. It's slightly out of place here, but this chemical structure here is utilized within our Poriatine macroporous mesh, Poriatine DS composite mesh, and then also our latest textile launch, which is Dextile anatomic mesh. This is designed for MIS inguinal hernia repair. It's made from polypropylene. Polypropylene meshes were first described as used for hernia repair back in 1958. Let's talk a little bit about absorbable polymers. Polylactide and polyglycolide are 2 different polymers in the polyester family. They're absorbable, and by absorbable, I mean that they have a backbone that is subject or available to be attacked by hydrolysis. So water can go up to this backbone and start to digest the polymer and break the chain. We can make copolymers of PLGA, where individual MER units, right here, are randomly arranged or in a more orderly fashion. So the building that I work in Connecticut takes glycolide monomer, monomer from lactic acid or lactide, dioxanone, TMC, and caprolactone, and makes copolymers out of them. And we take these copolymers and we can turn them into fibers, monofilament and multifilament fibers, through a process called extrusion. It's important to know this because these are the building blocks of meshes, these polymer fibers. We can do the same with polypropylene and polyester. Below here, you'll find a list of products that we use for polylactic acid and polyglycolic acid where they're found. ProGrip meshes have polylactide grips. That's 100% lactic acid, 100% lactide. Our Poritex composite ventral patch actually has a ring structure, and that ring structure is made of roughly 82% PLA and 18% PGA. Now, that same chemical composition is used in both AbsorbaTac and ReliaTac tackers. And many of the absorbable tackers that are out there in the market are PLA rich, around the 80 to 85% of PLA. What's really interesting is if you can take these different polymers and modify their chemistries in different components and be able to get different properties completely. The example of that was 82% lactide and 18% glycolide to make a tack with its durability and how long it takes to go away in the body. Likewise, if I take a 90% glycolide and 10% lactide composition, what you're going to be left with is roughly the composition that's used in Polysorb or Vicryl sutures. And it has a much shorter decomposition or absorbable time frame. So we talked about the underlying materials and the role that this material plays. Now let's start to understand how the surfaces of these materials influence the implant in terms of cell attachment and proliferation. When we first talk of attachment as cell adhesion, it's helpful to think of a cell as a droplet of water on a surface, as you can see to the right here. The underlying material property has a surface energy, and it dictates how the water droplet spreads out or beads up on the surface of the material. Hydrophobic materials, like PTFE, yield a beaded water droplet. This is helpful in situations where you would like a waterproof clothing or a nonstick surface for cooking. Polypropylene and polyester have more hydrophilic surfaces. They have much lower contact angles. They're shown to more readily promote cellular adhesion and proliferation. Hydrophilicity is also influential in how susceptible a surface is to bacterial colonization. When a biomaterial is implanted and there is bacteria present, there is a race to the surface between creating a layer of proliferating host cells and the biolayer of a bacteria. Globally, bacteria have the same objective as these host cells. The longer you keep bacteria away from the surface, the harder it becomes for bacteria to attach to your implant. So there is specifically a race to this surface. Please remember that this is about the biomaterial alone. And if we sit there and look at this as a flat biomaterial surface without any morphology, all of this can be adjusted and changed and varied with the characteristics of the implant, specifically the morphology of the mesh. Now we're going to take a more global view of the wound healing response. This is a response that happens anytime you have tissue trauma. The presence of a foreign body, like a mesh, will intensify this inflammatory response. There is a desire to control the intensity and time of the inflammatory response. This phase is needed, though. It's key for setting the stage for what we call the reconstructive phase. Initially, there's a release of fibrin. Some of the earliest factors of the inflammatory response are the arrival of some of these PMN cells, which are also just easily referred to as white blood cells. These get activated, arrive at the injury site, and they start sending signals out, recruiting other cells to arrive. Macrophages are another type of cells that arrive. They can be considered the conductor or the maestro of the orchestra. They play a role in releasing cytokines and removing cellular debris from this site. Fibroblasts hear these signals, and they arrive at the site of inflammation as well. These fibroblasts secrete collagen of different types, and that leads to the remodeling of the tissue. Capillaries are created within this remodeled tissue. We think of this, it's important to note that it's been shown that the tissue strength will never be as strong as the native tissue when we have this injury because of the collagen structure and the organization that forms due to this trauma is different than what was present at the time of development. This is why meshes are so important. They serve to buttress the repair during the inflammatory phase and also help support over long periods of time. Now, we've established that mesh is made of polymer fibers. We talked about how polymers are made. We've discussed what happens at the polymer surface and provided a brief overview of the wound healing response, which leads to the integration cascade. Now I want to take a step back and discuss how we manufacture our hernia meshes from polymer fibers. At Medtronic, this is done at our Trevoux Biotech's facility. We have a center of excellence of biotextiles in Trevoux, France. This is located about 30 to 40 minutes north of Lyon. It's a site where we have several functions: research and development, manufacturing, marketing, medical affairs, quality. At this facility, specifically, we make textiles. When we think about hernia meshes, a great majority of the meshes that we manufacture for hernia repair, regardless of company, are warp knitted textiles. It's important to describe these as warp knitting. This is a process that is not considered braiding or weaving, and even though those two terms have often been confused with this. Warp describes the machine direction of the knit. As you can see, this machine here, the size of this and the depth of this is about 1.5 meters in depth. If we look here, warp knit textiles have fibers or monofilaments that are all going in the same machine direction. As you can see, they're all heading in that same direction. Now, the opposite of a warp knitting would be weft, or a weft direction, and that's across the machine direction of the textile. It's important to note when you're doing warp knitting that there is no weft yarns that are placed like there would be in a loom for weaving. The distinction is that you could follow an individual filament from the bottom of this schematic here, and then it would exit out the top of the filament. There is nothing that is exiting out the sides of this mesh as we process it. Now, we use warp knitting primarily because it's a versatile manufacturing method. Every textile on the right side of this slide here can be created using warp knitting. It's important to have a manufacturing process that can give us such structural versatility. You can see that we can use single or multi-yarn types. We can use 2 dimensions or 3 dimensions. The top photos would be more 3-dimensional structures. We can control strength in elongation in both the warp and the weft direction. And we can create a variety of different pore sizes with these different geometries that are dimensionally stable. We can create gripped mesh. As you can see at the middle bottom picture right here, is an SEM micrograph, just to clarify. This has 2 different monofilaments in it. It has a polyester monofilament as well as a polylactide monofilament. The polylactide monofilament has been modified to create grips. So that is a pro-grip mesh that some people use. And lastly, one of the important things and the advantages of warp knitting is that surgeons can cut the edge of the mesh without having to worry about it unraveling. So I want to get back to this slide that I showed you earlier. We had focused on the polymer and how the knit is made. Now we're going to start to talk about porosity, the mesh weight or mesh density, and the mechanical properties. we find that there is a correlation between a textile's porosity and tissue ingrowth. Textiles have a microporosity, which influences cellular penetration. They also have a macroporosity, which plays a role in limiting fibrous encapsulation. We create textiles that have macropores that are greater than 1.5 millimeters in size. Additionally, warp knitting allows us to control the shape of the pore, and this is an influencer on the material response as well. Hexagonal pore shape has been shown to be more stable and not susceptible to deformation under strains. This is important because if we were to take a textile and pull it in one direction, we don't want the pores in that direction to collapse and shrink the size of the pore. Speaking of the macroporosity, the mechanism for this mesh shrinkage, as we've often heard it, is a contractile force that arises from the fibrous capsule that can form when the inflammation from the fibrous bridges around the individual filaments becomes too close. This happens when you can have less than 1 millimeter in pore size. As you can see from this histology slide here, these monofilament structures here, the actual inflammation around them merges with the inflammation around the other bundle of monofilaments. When these combine, they can create what is an encapsulation, and this fibrous bridging will serve to constrict the actual mesh and shrink it, appear to shrink it at least. We've shown that if you actually histologically and in studies that if you can actually control the pores above 1 to 1.5 millimeters, you can actually achieve proper tissue ingrowth where you can get proper infiltration of cells, and the actual the fibrotic capsule does not merge between the different monofilaments. So it is engineers and scientists and my colleagues, we go out and we speak with surgeons, and we hear surgeons tell us that mesh weight, and they talk about mesh weight as it's a very big indicator of properties. And they can say that they can look at a mesh and say, I can tell what the mesh weight is just by looking at the mesh and looking at the textile. This one's lightweight, this one's medium weight, this one's heavyweight. Surgeons often make a correlation between pore size and mesh weight. Unfortunately, there's not a direct correlation. While this can be the case for some materials, we want to describe mesh weight first. We're very familiar with mesh or density, and the density and the property of density in the 3 dimensions. This is essentially a mass over a unit volume, a cubicle or a cube or a sphere. Actually, if you were to displace it, you can get the volume, you can know the mass, and therefore you can figure out the density. For water, that's 1 gram per milliliter. When we think to the 2 dimensions, and this is the surface density, this is what we measure when we look at mesh weight. It's the mass of the mesh divided by the area of that textile. If we take this down to the 1 dimension, and for those who are, we look at this as a linear density, and this would be, say, a line or a filament or a suture. That actual suture has a length, and it can have a mass of that certain amount of length. For those who are familiar with the textile industry, this is often referred to that linear density as either the denier or the detex. That's how it's characterized. What we can see here, though, for this surface density, we compare 2 different ventral meshes that we have out, and one historical and one that is available today. We compare this to mesh A and mesh B. When we can look, we can say 78 grams per meter squared, and pore size that's between 2 and 2.5. For Symbotex, it's about a 66 grams per meter squared. And then the pore sizes are 2.3 by 3.3. When we look at mesh A, this correlations, it's true. You do have lower weight, and you can equal larger pores. So 3.5 by 3.4 with a 29 gram per meter squared. However, mesh B is a polypropylene monofilament, similar type of monofilament polypropylene. It actually has a low weight and small pores. So the correlation is not necessarily always there. So the ability to say, I can look at a mesh, look at the pore size and say, I know the density, or I can tell what the density is important. We believe that pore size is very important for how the material acts, how the host tissue responds to the mesh. Now, our team in Trevoux has mapped this out graphically. They've taken a smattering of different meshes that are commercially available. They've looked at pore size and they've graphed this against surface density. And they were finding that there was no correlation between the two. On the right, though, you can see tensile strength did have a correlation with surface density. And this sort of makes sense. The textile with more material per unit area could be stronger. So speaking of strength, we're often asked how much is enough. Often hear meshes are over-designed and how much safety factor is in there. Want you to know that Medtronic and other mesh manufacturers, we utilize relevant literature to describes the internal pressure that's within the abdominal wall. We take this, we utilize also finite element modeling to understand what this internal pressure equals with different layers in the abdominal cavity as well. Now, to get regulatory body approval, a company like Medtronic utilizes standardized and validated test methods for testing the mechanical properties. We look to design the mechanical properties, specifically the strength, into a mesh that is greater than or equal to that of a predicate device. And we look to the predicate device's complaint history to understand the clinical experience with that specific product in that application. So we've described how we manufacture mesh and how they have warp and weft directions. It shouldn't be a surprise to you that these different directions can have different mechanical properties. Now, our meshes are anisotropic by design, specifically our ventral meshes. With internal data and clinical data, we have set standards for these properties to ensure that the textiles work effectively if they're placed in either direction, though. In the ventral space, meshes are designed to have more deformation in the cranial-caudal direction and more strength in the transverse direction to match what's going on in the abdominal wall. For inguinal hernias, the direction of the biomechanical forces are not as well defined and they're not as well studied. The goal with these repairs has always been to have broad coverage of the myopectoneal orifice and for the repair to be done with minimal tension. Now I want to talk a little bit about how we measure the mechanical properties and how we design to these different mechanical properties. We design meshes that have a balance of mechanical properties. Here are a subset of the tests that we use to characterize mesh strength and compatibility with fixation means like tacks and sutures. What's important is how these meshes are being used in the body and what failure mechanisms they might encounter during the lifetime of implantation. I'm going to go through these individual tests and they're linked to the numbers above. So a basic tensile strength, anybody's taken a mechanical engineering class, it's taking a textile structure and holding one end constant and pulling the other end in a constant displacement, a constant strain rate. At the same time, a load cell is used or a scale is used to measure the stress that's generated as a result of that displacement. And from that, you can get ultimate breaking strength and stiffness and a number of different properties. Burst strength is another metric that is used. This is one of the standards that we use. There's probably 3 or 4 different burst strength tests that are out there that are utilized by different companies. This specifically takes the pressure through a bladder, that purple bladder, and it places it incident perpendicular to the surface of the mesh. This is a little just glass bell jar to suction that up. From this, you're able to look at the displacement and the stress that is created on a burst strength level. Number 3, we utilize a suture pullout strength. Similar to test 1, where you're using a tensile testing machine, you can actually take a suture and passage it through a mesh, through one little point there, and actually pull on that suture and keep the mesh constant and be able to see what that tractile force is to actually pull the suture out of the textile. So you're measuring at the pore level. Likewise, we test this with mesh tack shear strength. The example here is a basic commercially available mesh that we can test out. We test this right here with a Pro tack, and this is a piece of leather here that we're just using as a tissue substitute. We pull on the mesh, and we're able to understand at what point does the tack pull out of the leather, or B, when the actual textile pulls out of the tack. And the last one we test that we want to highlight here is tear strength. This is often referred to as the pant leg tear test. You can see that we fashion a slit in a piece of mesh. We put the different slits on either side of the tensile testing machine, and we pull on these. This is exactly a measure of how a tear or a micro tear within the mesh would actually propagate in the textile in vivo. So it's important to note that I can give you a mesh with a high ultimate tensile strength, and that it far exceeds the body, what the body will ever subject it to. But the problem is that mesh could have a very low flexibility and compliance and be uncomfortable to the patient. Likewise, I can have our engineers in Trevu make a mesh that has a tremendously high burst strength, far exceeding the requirements of any application in a hernia repair. But if the problem would be is that the suture pull-through strength of that same textile could be very low in a certain direction. I brought back that word direction. It's important to note that each of these methods, actually number 2, we don't. We test this in, it's incident to the mesh. But if we look to 1, 3, 4, and 5, these tests are all done in both the warp and the weft direction. Also, you'll note that these tests have been done and characterized by different ISO standards and different types of standards that are been established by testing agencies and developed by us specifically. Last, it's important to note that all of these tests are essentially describing single loading events. You take the mesh and you're actually pulling one load on it and you test it to failure. We know that meshes in the body aren't treated like this. They're not subjected to just single loading events. They're subjected to cyclic loading conditions within the body. We have begun to start to test our meshes and develop test methods to actually test these textiles in fatigue and design them to have both performance where they exceed performance standards in both the single loading events and that they have the long-term durability when they implanted in the body over many years. When we look to the mechanical properties, when we compare Poriatex optimized composite, Symbotex, and Mesh A and Mesh B, these other textiles, you can see that the direction, the anisotropy dependent, the directional dependent mechanical properties in this table are obvious. One thing I want you to take from this is direction is important. An example of this would be all of these meshes have different tensile breaking strength in the warp versus weft direction. It's most obvious with Mesh A and Mesh B, where it's more than double the actual force to actually break the textile. This is accompanied by a elongation under 50% or elongation under 50 newtons, which is measured as a percentage. This is a look at the flexibility or the extensibility. How much can this extend? how much this mesh could actually stretch, or the stretchability. You can see that for mesh B, the warp direction, if you're stretching this in the warp direction, 50 newtons would only equal a 14% change in the length of the mesh. But if you were to change this and test it in the opposite direction, a 50 Newton load will actually elicit a 107% change in elongation. That's a more than doubling of the length of the mesh. If we look to mesh A, another example of this, the tear strength, 22 newtons in the weft direction and 34 newtons in the warp direction. Why this is important is that even if your mesh is implanted in the correct anatomical structure, the correct anatomical direction, looking at the warp direction generally being across the transverse direction, there's shear forces in the abdominal wall that come from all different directions. So a mesh that is only as good as its weakest link, especially when it comes to suture pull-through strength and tear strength. Lastly, I wanted to comment on this and say that we recognize that mesh plays only one part in a successful hernia repair. There's growing body evidence that of the influence of a number of different factors. Obviously, it's being studied now, but it's always existed. But this is a complex equation. It comes down to the patient, what they're bringing to the surgical suite, the abdominal wall that you're working with, the surgeon and the training and the experience and the procedure volume, and the procedure that's chosen. All of this enters into a black box and leads us to have an outcome. And these successful outcomes, we understand that mesh is only one part of this. I'd like to thank you for your attention, and I am more than happy to answer any questions you might have.
Oh, hello.
Hello, Nathan.
Hello.
Hi, Dr. Dayas.
Hi. Well, my name is Jorge Dayas. I would like to thank Medtronic for sponsoring this session. Also to David Laurier for co-moderating it. And you cannot ask for a better partner than him. And finally, I want to congratulate GT for an extraordinary presentation. It was a comprehensive, educational, really presentation. You review the mesh essentials as promised from the molecule, I would say from the atoms to the patient. That was really enlightening to the surgeons who not all of us consider all these aspects. And it is important because surgeons should understand the full range of the physical, mechanical, and chemical properties of meshes as they affect clinical outcomes and patient reaction to meshes. There are other factors. You mentioned that correctly, the patient, the surgeon, the technique, but mesh is one of the most important, and we should know all these characteristics in order to apply the mesh to the patient and not the other side, the other way around. I would like to start the question and answer session with a question that you already, I think, answered, but I want to listen to your answer just again. Is anisotropy an important in inguinal hernia repair? You answered that. But why are most meshes for ventral hernia repair not factory marked according to the anisotropic properties? That's for JT.
Definitely. Thank you very much for that question. What we know that the classic within the IPOM mesh categories, that there are a number of IPOM meshes that actually have directional markings. I'm thinking a number of different ones that we have today. They have set directional, bias. It's assumed that these considerations for the ventral space are more important. But when we design our textiles, we design them in such a way that if a surgeon were to place them in the incorrect dimension or incorrect orientation, that they would still be fine. Next, it's important to note that there are a number of flat sheet meshes that actually are starting to have directionality to them. So it's important for surgeons to understand from the sales reps and from the scientists that they work with which direction the mesh is there. But we know that different types of flat sheet meshes that we use and IPOM meshes actually have a directional indication. And then just to add on to this, when we look to our ventral meshes or our IPOM meshes, many of them are prepackaged or cut in a elliptical or oval shapes. And these specific shapes are shaped to actually guide placement and positioning so that the oval is top to bottom from the cranial caudal perspective. So they're designed or cut to actually have the correct orientation when you take it out of the package.
Oh, thank you. I would like to ask you another question concerning the suture retention. That's for me a very important physical characteristic of the meshes that we should discuss, because we often suture meshes for fixation. How should a suture be placed? Parallel or perpendicular to the mesh greater dimension interthesis? So, for example, parietal light, does it matter to do it one way or the other?
It could matter. And I think the important thing is when you look at a properly designed textile, there's not going to be a weak link. If I were to consider a suture that's being held or at least perpendicularly passage through a mesh or through a textile, perpendicularly through that surface, if I were to pull that in one direction versus the other direction, that actual suture should not pull out significantly more in one direction than the other. It should meet a minimum requirement that we're looking for. And proprietary-wise, we have minimum requirements that we aim for when we're designing these textiles, so that the forces that you would find in the body and these shear forces on that actual suture would not cause the traction or the pulling or the ripping of those individual pores.
Okay, perfect. David, do you have a question for JT?
I just fascinating discussions, and thank you, JT. Just some follow-up on what we're already talking about. In surgeons' clinical practice, it's not uncommon for many of us to, for example, take a large rectangular or square sheet of flat mesh. Now I'm talking in the ventral space. And we find that the dimensions aren't quite long enough to what we need. And so we turn it in a diamond shape diagonally and thereby disregard the built-in isotropy or anisotropy. And there are some surgeons, for example, that, again, because the mesh isn't long enough, will use, say, a home base or home plate configuration where one portion of the mesh is square rectangular and the other is placed diamond shape with overlapping portions in, say, a huge ventral coverage. Mm-hmm. So kind of interesting to see the science behind the textile direction and how that might influence that. So the follow-up question I have to that as well, couple actually, is what limits and again, honestly, we're talking a little bit more about ventral mesh now. What limits the manufactured size, or at least the marketed size that you guys would put out on the market? For example, many of the meshes that we use in ventral hernias are maybe 30 by 35 in their largest centimeters in their largest dimension. There are a few manufacturers that go larger than that. Can you talk about what's involved with those decisions from an industry standpoint?
So technically, it comes down to the limitations on the size of a mesh come down to the manufacturing process. If I have a warp knitting machine that can create a textile width of 50 centimeters, I can make that. So there's very few limitations. It's just size of the warp knitting machine you have. But if we look to this, in the ventral hernia patient, use of very large meshes to buttress a large portion of the abdominal wall creates a much different biomechanical scenario than when mesh is used to protect, potentially fix a small defect. The surgeon is essentially asking the mesh to support a significant portion of the load on the abdominal wall in this situation. Additionally, these repairs that are done with these baseball diamond or creating it from stem to stern and from lateral side to lateral side, these techniques often involve significant dissection in the lateral compartments of the abdomen. And this could change the biomechanics as well. And there's very much, and we've talked about this a number of times, but there's a lack of basic science on an understanding of the effect of putting a very, very large piece of mesh in a patient and the procedures that require these very large meshes. We know about it.
So,
oh, please.
We need to develop that science then, because, from a surgeon standpoint, we think of this differently. When we are doing, say, a huge posterior component repair, like a TAR, and just as you described, from flank to flank and superior to the xiphoid down below the pubis, this is really more the concept of, from Stopa, of a giant prosthetic reinforcement of the peritoneal visceral sac, of the visceral sac. It is not the same thing as trying to overlap a medium-sized midline defect by 5 centimeters or more in all directions. Okay, so again, we agree the mechanics are different, but we are overlapping for different reasons, not for the same structural or say tensile strength. It may have to do with incorporation. Often for us, it has to do with releasing the tension on the actual, for example, midline defect more than supporting that all the way laterally with the same strength, if you will, compared to what's happening in the midline. So we do need to get together and discuss this. It almost seems as if industry, in bringing up some of the things which are new to many surgeons' thinking that you just did, and I thank you for that we really need to get together and discuss this and align, because we are being limited, and therefore we innovate, perhaps in the wrong ways, to deal with not having a big enough mesh. So definitely. Fascinating topics.
And when we think about this as well, especially when you think about these very large pieces of mesh, when that orientation, all of them are meeting a minimum spec that we're aiming for, if it's misused or used in the wrong direction. The last point that you made there on the body mechanics or the biomechanical considerations, especially with component release and especially with TARs, the body wall biomechanics is changed drastically with a TAR release. And this is something that surgeons recognize when they speak at congresses, and we need to understand how that biomechanical change actually affects or is actually reinforced or could be reinforced with these large pieces of textile.
So Jorge, that's a perfect lead. One of the pioneers in looking at some of these changes after these major component releases is here with us today, and that's Jorge Dayas. Jorge and Eric Pauli, Yuri Nowitzki, and others have done begun to do some really nice work into looking at what changes actually occur when we are actually destroying and cutting different layers of the and separating abdominal wall layers.
Yeah, well, in general, the lateral wall of the abdomen, when you divide one of the components, being the anterior or the posterior, there are two phenomena that compensate for that. One is there are overlapping in functions in these muscles. So you can divide one and the other can replace that function. And on the other side, we have found hypertrophy almost in all cases. So when you measure the width of the thickness of the lateral muscles after 1-2 years is really the same in the divided and the undivided than on the undivided side. So those two factors can compensate for the changes you may expect by dividing one of the components in the lateral abdomen. So probably the answer is, in the end, it's going to have the same physiology as the original abdomen.
It's fascinating. When we first study these things, we apply sometimes basic, sometimes quite complicated physics and mathematical models that tend to generally be relatively rigid models. And then we extrapolate that to a not only more flexible, but more importantly, a physiologic model that is adapting and changing and healing. And it doesn't always give us the same answers. And so we have to start somewhere, but we need to be cautious on that. I'm going to diverge into one of my interests, some of you may know, which is marine biology. And the perfect example was in the 1950s when scientists were trying to figure out how in the world does a dolphin, for example, swim so quickly through a thick, dense water. And they would drag these rigid models in the shape of a dolphin behind a boat with some ropes and figure out all these mathematical parameters. And it just didn't fit what was happening with the dolphins. And the reality is the dolphin's skin was flexible and changing and had sebaceous oil layers on top. And again, just much more complex than any rigid model that they were beginning to look at. So quite complex, the human body. There are some other questions to change subjects a little bit from the audience, several questions that have to do with JT looking at mesh when it's first implanted and then taking a look at it after it's been in the body for a while, and how does that change the burst strength, the tensile strength. There are even related questions to how does sterilization of the mesh, does that change some of those parameters even just before you implant it?
So from a sterilization perspective, there's different sterilization methods, ETO or gamma sterilization, and these are utilized with the different polymers. And I know that there are some minor changes or minor property changes of the textile with sterilization, but these are factored in within the design of the properties of the textile. When we look to polypropylene and polyester, these two materials are considered relatively inert within the body. So I don't have the extensive experience of doing explant studies and studying these textiles over long periods of time. But one thing to understand is that we need to understand the time effects of cyclic loading on these textiles. And that's why we've started this testing, to understand in a pseudo or a in vitro environment that we set up 37 degrees Celsius with certain serum. And if we're testing this, we're doing a burst test that mimic breathing or mimic coughing or sitting or the Valsalva maneuvers. We want to sit there and understand how this textile will change over time. And that's something that we're doing in the in vitro environment today with both polypropylene and polyester.
Many of the questions that we're asking today are fascinating, but very, very difficult to answer. Again, when you look at current explant studies that might look at mesh after it's been in a human body, not a lab animal, for a long period of time, these typically are meshes that were explanted because there was a problem. Okay, they're infected, there's chronic pain, there's contracture and fibrosis. So these likely don't represent the average or the normal value in someone that is not having a problem with mesh. So keep that in mind too when you look at some of these limited literature studies and look at what they've looked at histologically on explant meshes. Jorge, do you have some other questions?
Yeah, I have a question, as a matter of fact, on the mesh density, well, the biomechanical characteristics of the meshes. For example, let's go back to mesh A. mesh A has a low density. You can consider it light. The porous is a little bit large. And even though this very light mesh, when you analyze the biomechanical properties, almost all of them are above 15 newtons. That is really the minimum in the inguinal region. So why this tendency to use, for example, for large defects in the inguinal region, a high density mesh, if this very light mesh can compensate for all the parameters or the measurements?
It's definitely a great question. So when we think to these minimum requirements for mesh, it's also a balance of properties in what the surgeon is handling. So I could make a very, very lightweight mesh, 20 or 30 grams per meter squared, and I can roll that mesh up and place that down a port. But many surgeons will find that textile difficult to utilize because of the flexibility, and it would flop. So there's important to understand that a textile, or say an example would be the textile like Dextile, which is the anatomic mesh, or 3D Max. These are meant with, some of these have larger densities or higher densities. The importance to note is that the ability for that mesh to actually have some memory and be able to be usable and easy to manipulate within the MIS environment is also key. It's important not just for usability and to make the surgeon's job easier, but the easier the job that the surgeon has to be able to place and position the mesh dictates what coverage of that myopectoneal orifice is achieved. And we know that that is an important element of that inguinal hernia repair. So lots of different properties come into the play there. One of the important ones is to consider the usability and the ability for that mesh to actually be handled in vivo.
Let me follow up on that and ask you this. What is really the physical factor or factors of the mesh that determines memory? Because you mentioned density, but I heard that also the thickness of the mesh, the size of the fiber and others may influence that. And it is very important because rolling of meshes is related to two untoward effects. Well, one is recurrence and the other could be pain because it's rollover and it's not well integrated. So what are the factors that determine memory as we know it?
There's a number of factors. This could be textile design, the weight or density of the mesh, the material of the textile. We inherently know that polypropylene, if a same monofilament as a polyester monofilament, the polypropylene is going to be a little bit more rigid or bend a little bit, have a little bit more strength to bend it or force to bend it the same dimension. Also, it's based upon the manufacturing of this textile. As you said, the ability to roll the mesh, when we think about this, we want meshes to have a shape when they put them in. We want to roll them and pass them down ports, and then have them open up and become, compliant, and the ability to contour to the tissue when they're in the implanted MIS environment. A mesh could be designed that has too much memory, and it becomes completely, if it's a flat sheet mesh, becomes completely flat in the MIS environment. And that's not what we want. We want contouring to an anatomic shape. And partly that's why manufacturers create anatomically shaped mesh that is preformed somewhat to the set dimensions and the set shape of the inguinal environment.
Well, let me ask you another question that joins these two last ones. Let's say we have a preformed mesh with a low density or medium density, let's say 40 grams per square meter, and large porous, and all the biomechanical properties that are above 15 newtons. So why to create another preformed mesh heavier than that?
I think it's going to come down to surgeon preference. It's also going to come down to the surgeon's skill with being able to handle and manipulate the mesh and position the mesh in the MIS environment.
Okay. So this is a perfect lead into maybe we can have a little debate here clinically. Yeah. So I will say, because I hear a lot that, let's talk about just the inguinal space. I hear a lot of times the surgeons will say, well, you know, if I have a large direct inguinal hernia, then, you know, I'm definitely going to use a heavyweight mesh as opposed to a medium or lighter weight mesh. So before we get into this discussion, one nice clinical study that came out in the last year or so looked at mesh from one manufacturer. This was done at Carolinas Medical Center, now known as Atrium. And what they did, they looked at about 1,400 patients, and they compared from the same manufacturer a lightweight mesh that was 3D contoured. So that was about your 40 grams per meter squared, with the regular heavyweight version, which is roughly about 140 grams per meter squared. And what they found was they could find no difference in all of those patients in recurrence rates, in patient satisfaction or comfort scales, and in complication rates. And the recurrence rates, all comers, including many, many direct hernias, again, these were large numbers, 1,400 cases, was sub 1% recurrence rate in both categories. That was about 0.7 and 0.6% recurrence rate. So, you know, I think for me, that study showed that you can use a lightweight mesh or a heavyweight mesh. The choice is yours, but certainly it does not mean to me that you need to automatically switch to a heavyweight mesh if you have a direct hernia. In the next set of sessions for the SMART series, Dr. Dayas and I will talk through how to manage a large direct inguinal hernia and some of the techniques that you can do besides just switching a mesh. And so I will now vote in and say that in general, my preference, whether it's in the inguinal area or a flank hernia, is not to somehow up the weight, the heaviness, the density of the mesh to try and compensate for a bigger problem. My preference is to try and solve the problem, not get a heavier mesh. As JT has just shown us, the weight of mesh, I think, has been overemphasized with surgeons. And there are other characteristics of mesh that are actually probably far more important than, number one, the weight, and probably number two, the raw material used. And we'll get into that discussion in a moment. There are lots of questions from the audience on that. To me, and JT, I'd like to see if you agree, and Jorge, the porosity of the mesh, some of the structural characteristics you described in the textile weave, and the filament characteristics, monofilament versus multifilament, probably are more important than comparing a weight. And you mentioned that on one of your slides.
Yes, I completely agree. I think the textile design and how stable those pores are under minor tension in different directions. I believe that the inguinal hernia, if you consider from a direct or an indirect hernia, the implication is just where this hernia is coming and the amount of force that's being placed upon it. But it's important to understand that, you know, having some level, you do not want the mesh to strip. You want that mesh to be correctly placed and positioned within the inguinal environment.
Jorge, what are your feelings?
Well, I agree with what you both have said. On that respect, I think that all those characteristics should be part of the package, as has been suggested by many, because they are as important as the density of the mesh. Let me ask you a question. I think you didn't mention during the fantastic presentation what is the manufacturing strategy used to preform meshes? How do you preform a mesh?
So
Is that physical or chemical, or how do you do that?
So different companies use different methods. By preforming, we're discussing how we achieve an anatomic shape out of a textile, and it comes preformed in a specific anatomic shape. The different techniques that I know of are just straight up sewing them in a specific manner, thermoforming them or vacuum forming them, or taking two different textiles and welding them together. But you can imagine that these are manufacturing methods that companies hold close to their chest, specifically with respect to forming these anatomic meshes. But yes, there's a variety of techniques that can be used.
So it's an industrial secret, I would say.
Definitely.
It is very common amongst several manufacturers. We can see this welded outer rim of the mesh as well. That seems to be one way to keep it in. And I mention that because there are some surgeons that tend to customize that. They tend to cut away that edge in some products. The Dextile product that you guys have come out with is a very nice mesh, and purposely you have left off that, if I'm probably using the wrong term, but that welded fused border on the edge, and the area where it would go over Cooper's ligament and the medial portion of the iliacs. Purposely you've taken away that, so it's much more flexible and floppy.
Yeah, the welded edges on these anatomic meshes help with the retaining the shape and retaining the structure and that actual cup shape when they're placed, when they're rolled and placed through a 10 millimeter or an 8 millimeter port. When they spring open, you want them to have that same shape when they pop open.
We have a number of questions from the audience that all revolve around, let's compare polyester and polypropylene, and what are the pros and cons? JT, how do you answer those commonly asked questions?
Well, commonly when we think about polyester and polypropylene, and we create textiles that have clinical evidence and design these textiles that they have quality hernia repairs. We believe that the material property can be designed around it, at least from a perspective of flexibility and rigidity and mechanical properties of that, with different preferences of different surgeons. One thing to note is that when we've got a clinical evidence or clinical history of polyester in millions of patients, and also polypropylene has an extensive clinical, it's been extensively studied in clinical literature to be safe, and we can create good polymer or good hernia meshes out of either mesh or out of either base material.
I think that's really important for us as surgeons. It's very common to have this debate at national, international meetings, and you have strong feelings on either side, and people pick a favorite material. And the reality is these materials have been vetted, as JT says. So it's not that we could pick any material and say you can use anything, but given what we have available, and it's not just polyesters, as JT has shown you, there are many different kinds of that lumped into one term, polypropylenes, polyvinyl preparations of various kinds. The point is, I think that if you take an ideal polymer and you have the wrong pore size, or your textile design is not good, that could be a worse scenario than taking a suboptimal polymer, in other words, the raw material, but having a much better textile design and pore size. You're probably better off with the second example that I mentioned. At least that's my feeling. So I think we need to, as surgeons, sort of get off this ongoing battle of one raw material versus the other, when both are good. I would say in my practice, particularly in the inguinal area, and we need to educate ourselves more on the other mechanical and textile derived factors that are actually way more important than which specific of either good raw material was used.
This talk is my attempt at least to elevate that conversation and the topics of that conversation to be looking at that textile beyond just the base idea of its polyester versus polypropylene. And we know that there's been retrospective studies. I know Dr. Roth put out an analysis of this, looking back at the clinical outcomes of the different textiles, and found that the correlation wasn't there between outcome and material.
There is a question from Ed Felix that is very interesting, but I think already has been answered. He is telling us that probably the description of recurrences with lightweight meshes was not related to the weight at all. And well, JT has already answered that by saying probably the rolling of the mesh plays a part in these recurrences in lightweight meshes. It's not that the mesh is not strong enough to withstand the burst strength of the abdominal pressure, but that there are other factors related to how the mesh can change form or move immediately after surgery. So that question, I think, has been already answered, and I appreciate Dr. Felix being here. There is another topic I would like to discuss with David, and it is there is a different perspective that I noticed recently between the American public and the expert surgeons. There is a feelings that meshes are really dangerous. You can find that in the social media and even promoted by some surgeons. But when you ask surgeons with long experience, high volume of cases, or go to large registries, you find rarely that they have to remove mesh from the inguinal space. That's really rare. In my practice of over 3,000 inguinal hernia repairs, I don't remember having to remove a mesh because of the mesh reaction. So what's your take on this?
Yeah, I have several different takes on that. I think that's going to be a great discussion. The first thing is that you and I have practices that may be more like the average surgeon, and it is quite rare for us to see any mesh problems in the inguinal area. And we all say that individually, but our registries and certainly the incidence of chronic pain may belie that. And so if you're David Chen, if you're Brian Jacob in New York, if you're Shireen Tofi, and you do a lot of pain practice, then you're taking out mesh every other day, and sometimes multiple times a day. So that's sort of more an idea of contraction, perhaps poorly placed mesh, perhaps not a good enough understanding of how to minimize neuropathy, which we'll talk about in other portions of this series. The problem in the U.S., if I may be so bold, of course, stems from lawsuits. And so what we have is my patients ask about this on a daily basis. I'm sure all of us as surgeons deal with this in the hernia world. And I tell my patients when they ask, why when I turn on the TV, do I see 3 ads about how bad mesh is? And I say that generally I will describe 2 incidents to you where this stemmed from. And the lawyers are having a field day. And the first was in gynecologic procedures, particularly vaginal suspension, where the gynecologist would suture. Typically, it started off with relatively heavyweight polypropylene mesh to the vaginal cuff to elevate it, to suspend it for prolapse. And naturally, you might predict, or we certainly would, that you're going to have some erosion problems. And sure enough, they did, and they were horrendous. That has all been pulled off the market, and that has been abandoned, and other techniques are used. But the lawyers are making a lot of money off of that. The second major event, I believe, was this trend, and I think it started off with great intentions of many manufacturers going to lighter and lighter weight mesh with the ideas you've heard today of decreasing foreign body, less stiff, less plate-like scar formation and encapsulation, more flexible. And so we had medium and lighter weight meshes that actually perform quite well. And then some in the industry overshot that and made what we know as ultralight meshes. And in the ventral world, some of those parameters were overshot, and we started seeing some central mesh failure and things like this. And they weren't huge numbers, and people weren't getting sued. But in European registries, we saw, particularly with physio mesh, which had been pulled off the market, that there was a slightly higher recurrence rate with the ultralight mesh versus other meshes. So the large company with deep pockets that was quite responsible pulled that off the market. And the lawyers are now saying, hey, can your cousin, spell the word mesh? We can get you some money. Just give us a call, the toll-free number. So it's really spurred on by the legal environment. Now, I don't mean to gloss over this. They're clearly in the ventral space. If you put mesh in an infected field, or the mesh for whatever reason erodes or gets infected or is involved with bowel fistula, that can be disastrous. Okay. And so clearly mesh is not a freebie. There's certainly contraindications, and there's certainly complications that you need to inform your patients of. However, Jorge, I agree that in the properly done myopectoneal orifice critical view of dissection and a properly placed, properly sized mesh, it's going to be extraordinarily rare in practices like yours and mine for us to see any problems with the mesh. I mean, I can think back over probably 5,000 mesh patients for the inguinal area that I can think of maybe 2 people that have had any issues in my entire career. So
even the spectrum of pain varies according to the geographical areas, because to tell you the truth, it's not a big deal in Latin America. That pain is not, we don't find those percentages that are described, probably related because we are probably more conservative on the indications, because we don't operate patients with pain associated with hernia or other factors. Probably
you're either better surgeons or you have tougher patients than the whiny patients we have.
Probably they don't complain as much. That's another factor. But let me tell you that even pain varies as an effect of meshes, because we don't find those great percentages. Probably they say we don't follow the patients. But in my practice, I don't have to follow a patient with pain. He will follow me to the end of the world, for sure, if he has pain. So it's not that factor. What I try to say that in general, meshes are safe. Yeah, and we shouldn't change our practice or invent new procedures just because there are problems associated with meshes. But considering the great volume of surgeries we do worldwide, it is a small problem from my perspective. So,
very good. We'll take another 10 minutes or so. We could really go on all night about this. It's quite a fascinating topic. JT, I have a very specific question, and that has to do with your ProGrip product, which is a self-adhesive mesh with polyester backbone, if you will, and then grips that are long-term absorbable and go away. And we know in the United States that this is available on the polyester base, and that in Europe, I believe you have this also available on a polypropylene base. Can you comment on the differences in that scenario with polyester and polypropylene, and perhaps why that's in Europe and not the United States?
Yes, polypropylene and grip mesh, as you can pointed out, Pore ProGrip is available in Europe. But technically, as we can see, that polypropylene and grip PLA grips are not incompatible. It's important to note that polypropylene and polyester have different mechanical properties and different handling properties if you consider similar textile design. And we have to build this in utilizing different knitting patterns, proper knitting patterns to adjust for this. But technically, there's nothing that prevents that from being available. You would have to probably work with I would have to consult with my marketing department on understanding what the rationale.
So do you think it's more of a U.S. surgeon bias rather than the technical characteristics as to why you would have that in Europe and not, say, in the United States?
I think it's more of the market. Looking at it from a market perspective, I don't believe there's when we think about the polymer, if we think about the textile, there's nothing that prevents us from making something that has similar properties, or at least we can build into that polypropylene with ProGrip something so that would perform or act as similar to a lap ProGrip or a Pariatex ProGrip as well. So there's nothing that prevents that from happening.
JT, I have a question on plugs. Does Medtronic still manufacture plugs, and why? Why yes or why not?
I know that we have plugs within our legacy portfolio. I know that Pariatex plug and patch, I think, is there, and also SurgiPro plug and patch. I know that no technical engineering, work has been done on these recently, and partly this is because we, as a company and just as my personal feeling, I believe that there are a lot better hernia repairs out there, and I think the focus of being able to get an MIS hernia repair is actually paramount. So if personally, if I think about this, if I'm referring a relative to get a hernia repair, I will make sure, ask them to make sure that the surgeon is capable, they have good surgeon volume, but I would focus them on an MIS repair. I really can't speak, I'm not as familiar with the technical characteristics of the plug and patches we've had on the market, our legacy portfolio there.
Yeah, I read that probably the problems related to plugs are about shrinkage. They shrink as much as 60, 70%, so they can migrate. That may be the reason. And here's another question for you. How do you predict shrinkage of a mesh, of a product, and why is that important?
Yeah, so shrinkage is important when we, as I showed in that one schematic, if we govern the pore size of a certain pore size, we're not going to get the fibrous capsule or the individual fibrosis around a bundle of filaments and next to another bundle of filaments and bundle of filaments, that it won't at least it won't sit there and add to a contractile force on the mesh. Mesh shrinkage is something that we evaluate when we implant our products in large animal models during development. It's a part of the biocompatibility testing that we do. But as I said, it's driven by the pore size and the idea of the textile design being created so that it avoids this extensive fibrotic reaction. Lastly, if we think about this at the next level on a filament or an individual filament level, shrinkage can also be related to the material properties of that individual filament. And we test that for every filament that we use, every type of filament that we bring in. We understand that the properties of that filament in a shrinkage format. So something we study extensively, and we try by design of our textile and choice of filament to avoid this appearance of shrinkage, but it's preventing it from actually the body from remodeling this and creating what is potentially something that is a balled up fibrous capsule.
Okay. What is an acceptable percentage of shrinkage for a mesh? Is there an acceptable rate?
I don't know I know that there has been some studies that studied different types of ventral meshes on this, and some of them have up to 15%. I would have to check the literature on what those levels are. But I don't know of what if we measure this as a dimensional shrinkage implanted, I don't know what the acceptable limit is for this specific test.
I think the important part here is that each surgeon should understand the shrinkage rate amongst the other properties of the mesh they are using. For example, for probably 15 years, I used very inexpensive, flat sheet, heavyweight polypropylene mesh. This caused a flat scar formation, but this is very forgiving, relatively forgiving in the inguinal space. There are many surgeons that still use that. But that mesh shrank as much as 40%, almost half of its original size. And if you understand that and compensate that for a bigger mesh, you can get by with that. You're not forced to accept a 15% or less shrinkage rate, but it's very clear that you need to understand the material you're working with. And I would say to sort of begin to wrap this up for a few minutes, I would love to hear from both JT and Dr. Dayas. Can you summarize what you think are the ideal characteristics specifically of an inguinal mesh? I think the ventral space is actually more complex when it comes to mesh design. So maybe just in a few words, each of you sort of summarize what you think is important about inguinal mesh. Jorge, would you like to start?
Yeah, thank you. I would say it's a mesh which can be above the minimal biomechanical properties that we already discussed. The material is not so important. The size has to be at minimum of 15 by 10 centimeters and probably more in some cases. And it has to be easy to place without folding without folding mostly. And it has to have not great memory, so it doesn't roll. If it's preformed, well, I'm tending to prefer preformed meshes lately. I have found they are easier to place, and they most of them don't need fixation, even in medium-sized meshes. But that's a personal vision of those meshes. But in general, that's what I'm looking for a mesh, and obviously, not so expensive.
I hear that, you guys. JT, what are your? That's excellent, Jorge. Very good advice for all of our surgeons. JT, what are your thoughts as an engineer, having worked in this field so long and developing these products? What's the ideal inguinal mesh?
Well, just to touch on that last topic, at least really quickly, the shrinkage-wise of 40% is far more than what any spec will be on any ventral mesh. It's going to be much, much lower than that. But for the inguinal hernia or the mesh for the inguinal area, from an ideal characteristic standpoint, as I described, we want to promote rapid tissue ingrowth. We want this mesh to serve as a scaffold for which the actual host cells grow fibroblast into and actually remodel and create new collagen. Next is broad coverage of that myopectoneal orifice, making sure that we got coverage over all those areas. We want it made of biocompatible materials that are with a biomechanically viable textile structure. And last is the usability, and it's overstated often, but the ease of placement and positioning in that inguinal space. If I'm giving a mesh that is the best mesh ever, but it's difficult to use, then I have a problem, because I know my surgeons are not necessarily going to be placing that mesh and be willing to actually readjust and reposition that mesh in the correct orientation or in the correct and slightly move it. So I think it's important to have ease of placement and positioning and repositioning if needed.
Excellent. Well, again, I want to thank you along with Jorge for that excellent in-depth presentation. This is quite a bit more than we typically hear. We're just hitting the hour and a half mark here. I would throw my 2 cents in there for surgeons for inguinal mesh. The top manufacturers all make excellent inguinal meshes. You can likely use any of those products. And if you know what you're doing and you know the anatomy and you develop that critical view of the myopectoneal orifice and you develop your skill set, you're going to have excellent results regardless of any of the top meshes that you choose. So again, I would say large pore size and usually monofilament trump, whether it's polyester or polypropylene or anything else. And heavyweight, lightweight is not so critical. I think either one is fine. Now, please distinguish, we've had a number of questions and comments that there is literature looking at some of the ultralight meshing area. I'm going to throw out a brand name, for example, Ultra Pro. And the first version, not the advanced version that was quite light. And there is literature to show inferiority of that ultralight mesh compared to normal weight or heavyweight mesh. We're not talking about that these days, okay? We're talking about the lighter class, the midweight class, and the regular heavyweight class. And I think all of those are going to give you comparable results. The real, as David Chen says so well, the variable that none of us are controlling for in this excellent best practice in evidence-based medicine is the surgeon. And that is more important than any of these good meshes. And in the inguinal area, ventral's a different story. So I think to wrap this up, this is a perfect lead into next week's session, which is the critical view of the myopectoneal orifice, the insiders edition, because we have Jorge Dayas, and we are quite honored to have as our moderator for next week, Dr. Edward Felix. As you all already know, Drs. Dayas and Felix codified this critical view in their 2017 paper in Annals. And we can't emphasize the importance enough of that. And we're going to give you probably a more in-depth, detailed view of that than you have likely ever heard before. So we're quite excited about that session as well. We want to thank our sponsor, Medtronic, for allowing us to reach out to you. Thank you all for submitting your questions, and we look forward to seeing you next week.
Thank you. Thank you, JT. Thank you, David.